So right now we are standing in the molten salt research laboratory where we'll figure out the components, the soup that the nuclear fuel will be molten into in the molten salt nuclear reactor. So one common question we're asked is molten salt. So salt is similar to table salt, which is sodium chloride, but you can make salts out of a number of elements. So you can also use fluorides, and you can, instead of sodium, you can use beryllium and lithium. And so those are the types of elements that are utilized in these molten salt reactors. Then with the addition of either uranium or thorium as a nuclear fuel source. Also, here is a picture of University of Utah's Trigga research nuclear reactor, which is up in Salt Lake City. And you'll notice that you can see directly to the reactor. This reactor is actually critical, and it's under a pool of about 20 feet of water. And that picture can be taken by someone standing right next to the reactor without having any negative exposure. Whenever you have nuclear radiation emitted, the proper practice is to shield from it. And right now the water is acting as the shield, and you can stand safely without receiving any exposure. Water is good for stopping all the three types of alpha, beta, and gamma radiation. So when it comes to nuclear energy, the safe approach is to follow established procedures that are understood to keep the radiation away from human exposure, either in terms of shielding or containment. And we here at the center will dutifully follow all the proper procedures to keep the materials contained and radiation exposure below acceptable limits.
Okay, I'll ask a question.
So rather than build a full-scale nuclear reactor that produces power, right now we're researching the fundamental components of a nuclear reactor. For example, the molten salt in a molten salt reactor and how it affects the metal components of the structure, that can be studied without any nuclear fuel and just the salt components itself. And this lab is also, the Alpha Tech has developed the most advanced process for purifying these salts and is going to be producing and supplying those to other researchers nationwide. So that will be going on in this facility. And so next we'll take you to, we are now in the medical isotope or isotope research facility. There's one special thing about molten salt nuclear reactors is that the fuel itself is molten. In a typical nuclear reactor, you have a solid metal or ceramic pellet fuel, and then the coolant, usually water, passes over those pellets to acquire the heat. But in a molten salt reactor, the fuel itself is molten and travels in a circular path, where within the reactor it goes critical and produces heat, and then the bolt comes out to another heat exchanger where the heat can be extracted and then is returned to the reactor. And so one of the benefits of this design is that you can remove valuable components from that stream while the reactor is running. So for example, when a uranium or a thorium atom fissions, it creates a substantial portion, more than half of all of the elements on the periodic table. And when you think of the value of a lot of the different elements in the periodic table, there's many valuable things, such as the rare earth elements and palladium and strontium, and then there's still fuel left. So used nuclear fuel is typically over 90% usable fuel still. And then the balance, these other elements in the periodic table. So a nuclear reaction is like modern alchemy, taking one element and changing it into another valuable element that you can extract. The most valuable of which being elements that can be used to cure cancer, can be extracted from the fuel. And that's where Alpha Tech derived their name, was the alpha comes from targeted alpha therapy, from a certain element, isotope, that can be extracted and used in curing cancer procedures. So a molten salt nuclear reactor can kind of be viewed like the circulatory system in our body, where it's just going around and around, and you can eat and put the food in, or put the fuel in, which dissolves in the bloodstream. And then when it gets to the lungs, it releases gases that are no longer needed, and it goes to the kidneys. It releases other elements that are no longer needed, and those can be extracted and then used for other purposes. And in this application, for example, we often admire the Native Americans, who are known for utilizing a whole animal and all the parts, instead of just pulling off one particular part and throwing the rest to waste. So the same thing can be done here with used nuclear fuel. Rather than being viewed as waste, it can be viewed as a very useful item, where every component is put to some good, which dramatically reduces the amount that needs to be discarded in the end, and dramatically increases the value of that material coming out of a nuclear reactor. So that's what the type of research is that's done in this facility, in this isotope separation facility.